As Perry gets up and going, just wanted to say we are finishing up this afternoon. There will be some instructions at the end about how you will get the exam and when that's going to be due. So at this point, unless you've told me, if one person has said I do have to step out, I'm expecting you to be here for the rest of the class and engaged. And I did put my number, I'll put it in the chat, but I did send it to you all in an email if you have any technical difficulties during the class or issues and need to reach me. Some people haven't said anything. And again, if I don't hear from you and don't have any way to contact you, then you're just here, but you are not able to um, take the exam. And with that, Perry, I'll turn it over to you.
Okay. All right. Well, welcome back, everyone. So far today, we started out and had a lot of good discussion, I think, to kind of follow up on the first 2 days, Monday and Wednesday, and what we covered there in both the define phase and the measure phase. And then this morning we launched into the analyze phase. And we just remind ourselves that the key objective in the analyze phase is for us to be able to first identify the potential X's that are impacting our process and subsequently our process output, the Y. And then we want to work on then prioritizing those X's and getting down to the vital few X's. So the beginning of the analyze phase is really to come up with a comprehensive list. And you think in terms of like both brainstorming, but also we talked about some analytical type processes for being able to identify the potential X's in our process. And we can do that by going through what we call the data door, looking at graphical analysis and things of that nature to give some indications as to what factors may be related to our output. And then we also talked about going through the process door, and the emphasis there is on doing detailed process mapping to get a thorough understanding of the process. And that's always very valuable to anyone working with a process. And along the way, identifying specific measurables in and around the process. And then we talked about a couple of other tools, fishbone analysis and a YY analysis, to do a more qualitative assessment as to what factors are impacting our process and trying to get at kind of a root cause level of things that are linked to our process output. Any questions come up over lunchtime around the things that we covered this morning about both the process analysis and the data analysis? If not, then what we want to start with this afternoon is to talk about a cause and effect matrix. And like I said, what we're trying to do now is we've got a bunch of inputs, a bunch of potential X's, and we now want to look at, well, how can we prioritize this list and come up with identify what are the most significant X's to work with. And there's a variety of tools that are out there to enable us to prioritize work, prioritize programs, help us with decision making. And a lot of them are related to this whole relationship between cause and effect. We want to understand, first of all, what causes are related to the effect, and then what are the most likely causes that are resulting in the effects that we're seeing. So we're going to talk about a cause and effect matrix. And so what is it? It's a simple matrix that emphasizes the importance of understanding customer requirements. It prioritizes the impact of process input variables, known as X's, based on customer requirements, Y's. And it will use the process map as the source of the X's and the Y's. So somebody asked earlier when we were doing the process mapping, was our list of X's and Y's a prioritized list? That wasn't, but now we'll show you how we can, a way that we can look to prioritize X's and Y's. So we'll identify the main requirements, outputs of the process map. we'll sort and mark the priority factor for each output on a scale of 1 to 10. So a couple of things to kind of pay attention to in terms of this process, because this is kind of it's an analytical exercise that uses numbers and calculations. So when we think about the relative priorities of something, so how important is one thing to something else, we want to think of a scale of 1 to 10. And when we think about what's important to the customer, not all things are equal to our customer, so we want to prioritize the outputs or the customer requirements on a scale of 1 to 10. Then we want to identify all the process steps of the process map, and then we want to relate how these process steps impact the output. And the way in which we want to quantify the relationship between the input and the output is by saying that either it has like little to no impact, small impact, a medium level impact, or a high level impact. So for low level impacts, we want to rate things on a scale of say 0, 1, and 3. And a high level impact, we want to give it a score of 9. Now, let me just say here that there are, like I said, there's a variety of kind of prioritization type tools. And a lot of times people, including engineers, can be fairly indecisive. So you can ask somebody to rate something on a scale of, 0, 1, 3, 9. And people can't make up their minds as to whether or not it's a 3 or a 9, so they want to give it a 6. Well, it's very important that we stick to the restrictions and the guidelines of the selection criteria, because we want to be able to differentiate between the impacts of various inputs. So while we rate the overall priorities to the customer on a scale of 1 to 10, we want to truly differentiate how each item impacts that output. When we get the matrix built, we essentially multiply cross values with priority factors, come up with a score and add them up. So we'll show you how to do that. We'll go through an example. So let's say, for instance, we are running a coffee shop, okay? And so we're trying to see, well, what are the factors that contribute to a customer having a positive experience in a coffee shop? So what are some of the things that are important to a customer when they go to a coffee shop? So these would be our output variables. Well, obviously one of the things that's going to be important to the customer is the taste of the coffee. The quantity of the coffee could be important. The type of container that it's served in could be important. The speed of service could be important to the customer. So when we look at these output values, what are some of the inputs that impact our ability to deliver on these outputs? And we can have things like the type of coffee beans, the quantity of coffee grounds, the brew time, the cleanliness. There are various process steps. So if we actually did a process map of the coffee making process, where there's setup time, there's brewing the coffee, sometimes it doesn't get served right away, it gets held, and then ultimately you serve the coffee. So you would have gone through, and there would have been a detailed exercise on the process map for making a cup of coffee. We would have identified numerous inputs that go into making coffee, both the process inputs and process variables. Remember, process inputs would be the ingredients, the coffee beans, the water, the condiments. I don't know what you call sugar and cream, whether it's condiments or what you call those. And of course, those are the process variables. The brew time, how long do you allow the coffee to sit in the coffee pot before you serve it, type of a thing. So the way that a matrix works and what it looks like. So we can look at kind of a final product here, and we'll describe how do we get this matrix. But this is what the matrix might look like. So what you see, and this is an Excel spreadsheet. So up along the top, you'll see the factors that are important to the customer, like for instance, speed of service, taste, the ambience of the place, the cost associated with the cup of coffee. And those are the Y's, and you can see X's: bean type, brew type, amount of grounds, cleanliness of the shop, water temperature, and whether you use a styrofoam or designer cup. And what we ultimately want to get to is the score on the right-hand side, which is a priority ranking. And in this case, the higher score indicates the higher priority. So how do we build this matrix? Because obviously we've come up with a system here that helps us to determine which of the X's are most critical and which ones are the ones that we really need to work on to drive customer satisfaction. So let's break down the elements of the cause and effect matrix. So number one is you list the outputs, and you always start with the voice of the customer. So what is the customer asking for? And in this case, like I said, we can choose a number of factors, but let's just say speed of service, the taste of the coffee, having a peaceful ambience or in a place with Wi-Fi or whatever, and the cost of the cup of coffee. The second step is to then rank the importance of these outputs to the customer on a scale of 1 to 10, with 10 being the most important. And here, obviously, you probably want to ask the customer, get a sense for what's really important to them. So let's say, for instance, we've done some work with focus groups, or we've gotten some results of surveys and things like that. And what we came up with was that most important was taste, and people gave that a 9. And the environment in the coffee shop and the cost of the cup of coffee were both rated, fairly important. So they were each given a 6. The speed of service, was given a 3. So let's just say, for instance, on a scale of 1 to 10, these are the relative levels of importance of the CTQs to the customer. And like I said, this of course varies from customer to customer, but say, for instance, like I said, you've done some focus group studies, you've collected a bunch of surveys, and as you aggregate the data, this is what you come up with for your customers. So now the question is, what do you focus on in your process to deliver the highest level of customer satisfaction that you can? So in step 3, you list your inputs. You list the brew type. These are your X's, the brew type, the bean type, the amount of grounds, the cleanliness of the shop, the water temperature, and what type of cup you use. Then comes the grunt work. Okay. So what you're trying to do is you want to correlate customer requirements to the process input variables. And this is a subjective exercise. There may not, in some cases, there can be some processes where there's a direct relationship between a process variable and an output, in which case then you would take that data analysis into consideration and determine whether or not you've got one of the key inputs. But in most cases, it's a subjective exercise. So what you want to do is you want to get the team together and reach a team consensus of how the input relates to the output. And this is the exercise that is typically the most time consuming. And the first thing you do is you agree on the criteria for each score. So one way to do this is you say 0 means that there's no relationship between the input and the output. And that's very possible. It could be that the process requirement only remotely affects the customer requirement. In other words, the input just remotely affects the output. A 3 would say that the input variable has a moderate effect on the customer requirement. And a 9 says that the input variable has a direct and a strong effect on the customer requirement. As I said earlier, this is a rough estimate. You want to avoid a final resolution. So if the team gets stuck, and can't agree on whether it's a 3 or a 9, force them to agree on one or the other. Some people do this with a 1, 3, 6, 9 score. I like to use the 0 because there can be factors that really have no relationship to the output. but they may have an impact on one of the other outputs. So in this case, we're going to use 0139 as our scoring system. So remember, 0 is no correlation. 1, process input only remotely affects the customer requirement. 3 has a moderate effect, and 9 has a strong effect. So let's look at the scores that we may have come up with. So for instance here, we will say that the type of bean used doesn't impact the speed of service. It doesn't matter which kind of bean you have. The speed is going to be the same. The type of bean definitely impacts the taste. Bean also doesn't affect the ambiance of the place. But beans definitely affect the cost. Some beans are much more expensive than others. So beans have a strong impact on taste and cost. They don't have an impact on speed of service or ambiance. The type of brew, the way in which you go about brewing the coffee, it definitely impacts the speed. It definitely impacts the taste. Doesn't really have an impact on the ambiance, and it has a moderate impact on the cost. The amount of grounds that you use, once again, doesn't impact the speed, definitely impacts the taste because it makes the coffee either strong or weak. Doesn't impact the ambiance, and it has a moderate impact on cost. The type of bean has a big impact on cost because some beans are really expensive. The quantity of beans, of grounds, has a moderate impact on cost. The cleanliness of the shop has a weak impact on speed of service. I mean, you actually spend a little bit of time cleaning up the shop that may take away time that you have to actually prepare coffee, but for the most part, it would have just a small impact. The cleanliness of the shop doesn't impact the taste of the coffee unless you count in the cleanliness of the coffee pot as being part of the cleanliness of the shop. But we're talking about the floor and the walls and the tables and stuff. The cleanliness of the shop definitely contributes heavily to the ambiance of the place. And it doesn't contribute to the cost. Water temperature doesn't impact the speed. It does impact the taste, doesn't impact the ambiance, and it has a moderate impact on the cost. And whether you use styrofoam or paper cups doesn't impact the speed of service, doesn't impact the taste. Some people think that using the designer cups or holiday cups this time of year does add to the ambiance. The type of cup does add to the cost. So now that you've got this grid filled out, now you do the mathematics. And what you do is you multiply each correlation rating by the corresponding importance ratings of the Y. You add up the products. So in other words, you multiply 0 times 3, then 9 times 9, 0 times 6, and 9 times 6. And you add those 4 numbers together, and it gives you 135. Then you multiply the 9 times the 3, the 9 times the 9, the 0 times the 6, and the 3 times the 6, and you add those 4 numbers together and you get 126. And you just go on throughout the matrix doing that calculation. And so what you come up with is a final score, a relative rating and a final score. 135 for the bean type, 126 for the brew type, 99 for the amount of grounds, 57 for the cleanliness, 99 for water temperature, 72 for type of cup. And you would then rank order these, so sort them by, go from high to low, and you determine what the break point is. So you may say we only need to focus on our top 3, or you may have done this exercise and there could be 20 X's in the list. And you may decide that the top 5 X's are the most critical. And those are the ones that you choose to focus on and carry forward into your future analyses. But this is a tool, and I'll point out that it's not just a valuable tool for, in this case, we are trying to determine which factors, which X's have the biggest impact on the Y's that we are trying to fix. But this whole concept of a cause and effect matrix using this kind of a scoring system, it can be used to make decisions on, and prioritize projects. For instance, you could make a decision on if you're buying a home, if you're buying a house, you could use this type of a matrix to determine which house, you may look at a dozen houses, which house is best suited for your family. So along the top here, you would have things like what's important to your family in terms of a house. One could be location, one could be price, one could be proximity of the schools, one could be property taxes, one could be space or features. Then you rate these on a scale of 1 to 10. What's most important to your family? You may not have young kids, so proximity to a school would be of little importance. Or you may have several kids in school, and being part of a really good school system could be one of the higher criteria. So you would rate what's important to you in terms of purchasing a home on a scale of 1 to 10 along the top here, and then you would list the individual houses that you looked at as your X's. So this is house on 2236 Bourbon Street, and this is the house on Main Avenue or whatever. And then you would say, well, this house on a scale of 0, 1, 3, 9, it rates, a 3 on location. It's in a really good school system, so we'll give it a 9 here. It's has a very high price, so it gets a 1 here. And then you do the math, and it'll tell you here which are your top choices for homes that meet the criteria which are most important to your family. So this is a very valuable and effective tool for helping you to prioritize things. In this case, helping you to prioritize which X's are the most critical, because all of the X's may have some impact, or else you probably wouldn't have put them on the list in the first place. But you don't need to work on everything. You just want to identify the 3, 4, or 5 most important factors, and those are the ones that you're going to quote unquote fix to get better control of your output. So I'll pause here to see if you have questions or comments about this concept of a cause and effect matrix.
I'm not sure if I fully understood what the breaking or the break point was.
Okay, the break point is, so you'll end up with a column of numbers here, in the total priorities column. Okay, and like I said, in this case, we just had 6 X's, and it could have been a list of 20 X's. All right, so once you get it sorted, so now the question is, well, okay, I've got this list of 20 X's, and the highest one has a score of 135 and the lowest one has a score of 22. So which ones do I consider to be the most important? And there you decide. In this case, you may say that, okay, I've got 4 of them here, 135, 126, I got a 99 and a 99. And you may decide that 99 to 72 is my break point. I don't need to look below 99. Okay, and that gives me my top 4. Or you may have decided that I'm only going to look for those X's that have a score of 100 or above, in which case you're only going to focus on bean type and brew type. So the break point is the decision you make on which ones are the highest priority. So obviously, if you have 2 that are fairly closely in score to each other, bean type and brew type, for example, then you would leave both of those in play. And you may even say that the amount of grounds and the water temperature are also significant enough that you want to leave those, in contention for being significant impactors. But you'll say this has a score of 57. That's quite a ways removed from 135 or 126. So we won't really worry about the cleanliness of the store. And we're not even going to worry about the type of cup, because 72 is quite a ways away from 126. So the break point is, like I said, the decision that you make about which ones to consider and which ones you're not going to worry about as in trying to solve the problem.
And Perry, let me just chime in too and mention, and I also see your hand, Nicholas. Money, that drives a lot of decisions in business. Like, for example, I recently went to a coffee shop. They did not have the bean I wanted, so I did not want to get anything. But they couldn't get it. There was some supply issues. So there are other factors that, if you're actually using this in a real world application, that may drive your decisions. If you don't have enough workers during the pandemic, there were a lot of places that didn't have enough people to actually stay open for the number of hours that they used to have. So that might say, well, you know what, we're not going to worry about some factors based on the fact that we don't really have enough people to make money off of having that anyway. You'll have enough workers to make that feasible. So that's, again, it depends. There's other factors that come into play when you're actually using this in a real world application to make decisions. And
Right.
Nicholas has a question.
Yes, I was asking for the CNE matrix. Is this the only template it comes in, or is there different, I guess I would say, formats to it?
There can be a wide, there can be a variety of formats, but this is kind of the concept here is pretty consistent. In other words, you put the factors that you're evaluating along the top, and you put the inputs along the side. So and in most cases, it's also that you prioritize things on a scale of 1 to 10, and you can correlate factors, and there can be different approaches. Here we're saying use 0, 1, 3, 9. Some people use 1, 3, 6, 9. So there can be variations of it, but this is a pretty standardized template, that one would use. In some cases, you just have like maybe just one, the key variable that you're looking at, and you may have some like this. You could have your output Y, and you could have some intermediate Ys. So it could get a little bit more complex in how it's structured, because the intermediate Ys impact the output Y. But you could consider all of those in the matrix. It depends, like, especially if you're dealing with a technical matrix, where, like, for instance, you're really correlating the relationship between process inputs to measured outputs. Then this exercise becomes a bit more scientific, because now you're needing engineering expertise to explain the relationship between viscosity and yarn strength, something like that. So there you would need the technical expertise to understand that, to be able to then properly input which of my process variables are having the big on my output. But here's the other thing. So, and we're going to follow this up, and I'm going to talk about hypothesis testing. So that's kind of like we've been collecting data on what are the inputs. This is one of several processes for how to prioritize the inputs. But another answer to your question is, another technique that people use for prioritizing things is like a failure mode effect analysis. and it's got a different template. So what a failure mode effect analysis does is it identifies what can go wrong in your process. So what are the various failure modes in your process? And then you would assess what are the likely causes of those failure modes. And then you assess what is the consequence of that failure mode. So if this does fail, how severe is the consequence? What is the probability of failure? How likely is it to fail? And 3, what is your ability to detect that a failure is coming? So you have a scoring system where you now assess the consequence of failure, the probability of failure, and the ability to detect your failure before it comes. And it's a similar concept. You cross multiply a bunch of stuff and come up with scores. And those things that have the highest score will, of course, be the things that you need to prioritize in terms of fixing. And it's the failure mode effect analysis is used to assess, how can you have catastrophic failures that could potentially result in a loss of life or loss of equipment and things like that. What's the likelihood of that happening? What kind of detection systems do I have? Do I have smoke detectors in the house that tell me whether or not there's a fire that might be coming, type of a thing? And if I have smoke detectors, it reduces my risk. If I don't overload the lights on my Christmas tree, it reduces my risk of the tree catching on fire, type of a thing. So there are other templates or formats that basically accomplish the same type of an objective. They're cause and effect matrices that enable you to calculate a score that helps you to prioritize potential causes for problems, or they could be for positive things also.
And just to kind of add on to what Perry is saying, just so you all know, there's a huge body of knowledge. We're not going to cover all of that in Yellow Belt. This is just the beginning. Again, you're on residential streets right now. You're not on the highway yet. So some of those are highway tools. But yes, there's a wide variety of tools. There's templates out there that are already set up in like Excel and some free software. Some stuff is free. If I see stuff, I'll pop it in. But something that I think Perry and I need to do with the process is try to recommend a tool set and templates so that you can easily navigate. Like you can have a toolbox. We're teaching you the concepts, but we're not necessarily saying here's an exact tool template to go use. There's a lot of them out there and there's some variations. So to know that, and you get similar outputs from maybe some different versions of them.
Right. And it's interesting because some of these tools, like things like failure mode effect analyses and things like that, some of those types of tools really came into existence in like the early 80s. For those of us who were around back then, there was a major chemical plant explosion in Bhopal, India, that killed thousands of people. And that kind of alerted the whole chemical industry around the world that, hey, we've got to be able to figure out what series of events can happen to result in such a catastrophic incident. And many chemical companies changed their standards and found proactive ways of assessing their processes to be able to predict, failure rates. And FMEA was one of the things that came out of that. So it's not it's a tool that's still widely used for for instance, we talk about it in the context of the Society of Black Engineers, because we're I mentioned earlier how people like to migrate to the shiny new thing, the new software package, or the new, virtual meeting platform or whatever, because they are attracted to the new features and they just want to do something different. One of the things we oftentimes fail to do when we assess whether or not to get the new thing, we'll usually take into consideration something like cost, like what it costs to buy the new thing. But we rarely consider what can go wrong by switching from our current system to the new system. And then usually what happens is when you then implement a new thing, people lose information and bugs show up and things go wrong. But we didn't anticipate it, but we could have. So we encourage people to use things like failure mode effect analysis. And actually, I'll oftentimes reference in this training. So we're just hearing about concepts here. If you follow through and go through Greenbelt training, you will actually use a C&E matrix, and you will put together a C&E matrix to help prioritize factors. And at least by the time you get to black belt training, you will actually also use like a failure mode effect analysis to potentially test out whether the solution that you've come up with, whether or not you might be creating some consequential metrics. Remember, on Monday, we talked about 3 types of metrics: your primary metric, your secondary metric, and consequential metric, where your primary metric is the main thing that you're trying to fix. The secondary metric is an added benefit that you get by fixing your primary problem. But the consequential metric is something that, what can go wrong? Like, for instance, if I go and buy the cheaper raw material and save the business a whole bunch of money, what could go wrong if I do that? And part of it could be that it doesn't work as well, or the part of it could be introduce a contaminant that I wasn't aware of. By doing a failure mode effect analysis, you assess that risk of doing that. So these tools are out there as you continue to, if you choose to go down the road of making yourself knowledgeable and developing expertise in Six Sigma, you will find yourself using and applying more and more of these tools. But like I said, there's a variety of things out there that can help you to prioritize things. But the concept of the C&E matrix is similar.
Perry, I'll just say one quick thing about the FMEA. Out of all the things I recall from just being an engineer for 25 years, that is one of the most useful tools. I don't think the colleges are teaching it. Some are hit or miss. But if you're going to be an engineer, whether it's transactional stuff or a product, you need to understand how to do an FMEA. It saves careers. It reveals risk. I won't go into detail, but Dr. Rona McNair was a fallen astronaut. The Challenger space shuttle explosion that designed FEMA said he should not fly. The engineer said, well, not just him, but the whole crew, we shouldn't launch. But a decision was made to go ahead and do it. They overruled, I guess some higher up said, hey, look, it costs us $1 million, some crazy number a day that we go to the launch pad and don't do it. But the design FEMA said, we don't understand how this O-ring is going to behave at freezing temperature. And that 1 degree made the difference in whether these people survived or not. So it's very important to understand risk and mitigate. That's what you do as an engineer. You can be creative and design stuff, but if it fails, you should not be surprised at the failure. And whenever I was in the quality world, if we had to work on something, my very first question to design engineer, are you surprised at this failure? If they are surprised that they not do a good job on the design FEMA. All right, quick question, then we got to move forward. I see a hand up.
Oh, so when they did that, so they didn't have like a quality control officer or something for the.
Oh yeah,
They
had
lots.
it was a matter of ethics. Go ahead, Perry.
Oh,
I mean, they had lots and lots of scientists that went into the design.
Mhm.
They did overlook or underestimate a critical factor, which was kind of an unknown for them, because at the end of the day, it was unusually cold weather in Florida,
Right.
which was not anticipated. But that's the whole point of the FMEA. You ask
Right.
what can go wrong and what's the likelihood of it.
Right.
And then how serious are the consequences. And it was something that they overlooked in assessing the risks. But they had, I mean, you can imagine they looked at all kinds of things, like re-entry and how things would heat up. I mean, there's this is rocket science, but you can overlook what seems like a minor detail, and and it can be catastrophic.
Yeah, one of my managers, a prior manager of mine, who I did not get along well with, now I understand why, he was an intern on that. And there were people who were saying, since we don't understand, there's too much ambiguity here, let's err on the side of caution. There were people who did not want to do it, and there was some who did. So, but that's a whole nother class.
Right.
We could have a whole class just for using the FPN.
Yep. Other questions about cause and effect matrix? I encourage you to try this out, and you can use something basic that's relatable to you and your home, your family or whatever. You know, think about buying a car or buying a house or some decision that you would make that involves several things that are important to you, and kind of go through this exercise with like your family or your friends or something like that, and say what's more important, and then look at the different options and do this assessment and this calculation and see what it comes out to be for the top option, just to kind of get familiar with the tool. So it's very practical, and it can help with a number of things besides just working on Six Sigma projects. All right. Okay. Let's talk about hypothesis testing. And I always throw out the phrase that, thank you for sharing your opinion, but show me the data. And Six Sigma, the neat thing is, at the end of the day, it enables you to take all the emotions out of whatever the issue or the discussion is, and you break it down to numbers. So hypothesis testing is essentially where people may have a belief about something, like this is important, or this is what's causing the problem, or this is a factor, and the question is, what does the data show us? And hypothesis testing is a way of doing a specific calculation that tells you either it is or it isn't. Okay, so let's kind of go through, and we're just going to introduce the topic here. Once again, for people who go on to Greenbelt training, you actually apply this, because this is, like I said, this is where the rubber meets the road. But you at least need to understand the concept here. So we went through in the analyzed phase, and we talked about how we can use various techniques to give us indications of what factors, what inputs are related to your output. And one of the ways in which we can do that is through graphical analysis. So we may look at a variety of graphs, and here's some examples in the pictures here. And they may give us a visual picture that suggests some relationship. And in many cases, that visual picture, like the picture's worth 1,000 words, that visual picture can tell us a lot. But even the visual picture may not be able to give us the concrete information that we need, or the concrete conclusion that we need to be able to draw. But we can analyze the data associated with those pictures and tell us whether or not there is a relationship between an X and a Y. So like, for instance, in the picture here, like the histogram, it looks like we've got dual populations here. In the box plot, group B looks like it's higher than the other groups. So hypothesis testing, it's a way to help us judge if the evidence is sufficiently strong to consider the X as one of the vital few. So in other words, the graph is telling us that this particular X is significant and that we ought to include it in our list of the 4 or 5 that we focus on. Hypothesis testing will confirm whether or not that's true. And we'll think in terms of this, we have this picture of this judge here because it's the judge. It is really a judgment type of a process. So let's introduce hypothesis testing. Now, a hypothesis is a tentative explanation that accounts for a set of facts that can be tested by further investigation. So if for any of us who've done like experiments in science, like when we going through elementary school and junior high school and even in the high school, or if you ever participated in a science fair, it all starts with a hypothesis. I think that if I give my plants more sunlight, they're going to grow faster. That's my hypothesis. Now I've got to run some tests and experiments to prove that. So hypothesis testing is a set of statistical tools that's used to determine the probabilities of that the proposed hypothesis given on an observed data set. So it's a set of tools that basically calculates the probability that your hypothesis is correct. So these tests are typically conducted on samples from one or more populations and are used to determine whether the observed data could realistically have come from the hypothetical population. Because remember, statistics is you take a sample and you use that sample and analyze it to draw a conclusion about the population. So in this case, the question is, I've got this sample here. Did this sample really come from my population? And hypothesis testing confirms that. So the purpose is to provide an objective basis for evaluating the evidence in our data. Objective versus subjective. Subjective is opinions. Objective means by data. It's to help us determine if what we think we see in the graphical display is strongly supported by the data, and to help us to quantify the risk that our conclusion might be incorrect. Remember, we're not doing 100% testing of stuff. So we're always going to be using the analysis of a sample to draw a conclusion about the whole population. But the hypothesis testing tells us what's the risk of having drawn the wrong conclusion. Now, hypothesis tests can help us answer the practical question, is there a real difference between the averages of two or more groups, or the spread and the variation in one group and the spread in another group, or that the proportion of defects in one group is different from the proportion of defects in another group, or the average count or rate of occurrence in one group is different from the average count or in another group. In some cases, you may think it's obvious. If I calculate the average of this and I calculate the average of something else, whichever average is higher is just higher, right? But remember what we said when we were talking about the different measures, and sometimes you use the average and sometimes you use the median to compare like populations. Like for instance, if we're looking at average salaries of people in say Washington State versus average salaries of people in Wyoming. Well, you may conclude that the average salary of people in Washington State is higher than that of people in Wyoming. But then you've got people like Bill Gates and others who live in Washington State. I'm just making this up. So he's really driving up the average. So while you may think that if I live in Washington versus Wyoming, I'm gonna make a higher salary, but what the average is really driven by the fact that you've got a couple of people getting paid a whole bunch of money, but that doesn't mean that you're going to get paid that much money. What hypothesis testing does for you is it tells you whether there's a statistically significant difference between those, and it confirms with statistics as to whether or not what the numbers appear to be telling you is actually true. So let's kind of get into it. So remember, we have a population and we have some kind of a sampling scheme. Like, if we're producing, 1,000 parts a day, we're not going to test them all, but we may choose to randomly select 10 parts each day and test them to make sure that the process is operating consistently. So we have some kind of a sampling scheme. We analyze those samples, we measure them, we collect data. And the hypothesis testing helps to determine if what we see in the sample is likely true of the whole population. So in other words, those 10 samples that we pull out every day, are they truly a reflection of what's going on with the entire production for that day? So when do we use hypothesis testing? Well, if we want to analyze inputs to determine if they affect a given output. Like for instance, we said we saw a bar graph that showed that waste levels appear to be higher in June, July, and August than they are in other months of the year. So we may form a hypothesis that our waste levels go up when the daily temperature is higher. So we can analyze data to see whether or not that's a correct conclusion, whether or not the reason why waste is higher in June, July, and August is due to temperature or humidity. Or we can have two different processes and we want to know if one is producing a different result from another one. Or if we want to know if one team is producing a better result than another one. Or if we want to validate an improvement before implementing it. You know, I'll use kind of like a football example because I watch ESPN a lot and people have been talking a lot about, you know, they of course analyze all the football teams. So one of the debates has been, so the Dallas Cowboys were like, they were on a 3 or 4 game winning streak after not looking good for a couple of games. And so now people want to talk about, and when they weren't playing that well, but a lot of people put the blame on the quarterback, Dak Prescott. But then they had 3 or 4 games where they played really well and he had really good numbers. And now they're saying he's one of the best quarterbacks in the league. So the question is, okay, is that actually true? And so one of the arguments is that, well, the 3 teams that he played when they won very easily and he had outstanding numbers were teams like the New York Giants and the Washington Commanders and the Tennessee Titans, teams that had really bad and they were losing records. So the point is that, you know, you can look at and I'm not going to try to draw a conclusion about the Dallas Cowboys, Dak Prescott, but the point here is that on the surface, the data may seem to suggest something else, may suggest one thing. But if you've got a team that's really beating up on all the teams that aren't very good, but you got another team that's losing to teams that are very good, just because one team has a better one-loss record doesn't mean that they're a better team than the team that happens to be losing to better players. So hypothesis testing is a way of collecting the data, analyzing it, and coming up with the right conclusion. So anytime you want to make decisions from a sample on an objective rather than a subjective gut feel basis, we use hypothesis testing. So there are a number of different types of hypothesis tests. So the question is, which test should be used? I just put this up here just to kind of give you an illustration of when you get into statistics and when you get into statistical software programs, it's not like you just have one type of test that you run. There are dozens of tests, and it all depends on what kind of test you want to use, and it's based on the types of data that you have. And I just put this up here because remember, a thing that I emphasize that you have to learn early on is whether or not you are using continuous data versus discrete data. Because the decision as to, and some of these names, probably most of these names mean absolutely nothing to you unless you've actually done some work with statistics. Some people may have heard of an analysis of variance, and some of you may have heard about a regression analysis. But most of you may not have heard about a one sample t-test or whatever. That's not so you would learn about that in like green belt training or black belt training. But the point here is that depending on whether you have a continuous X variable and a discrete Y, that will determine which of these tests you should use, or whether you have a continuous Y and 4 levels of a discrete X will dictate which of these tests you should use. So that's kind of the point of this graph. There's a variety of tools out there, which one to use and which one you put into your statistical software program is dependent on the type of data, the type of variable that you're working with. So the basic terms of hypothesis testing. And here I'm going to just kind of recommend that you guys kind of buckle your seatbelts and get ready to go along for the ride, because I'm going to describe this to you, and at the way the description comes out, it won't follow classical logic. And part of it, I'll kind of qualify it. Remember I said that the hypothesis testing is kind of like a process with a judge. And when you're in the courtroom, they don't always say things directly. They have to say things in such a way that you won't get in trouble for having said something that's false. So they have there's a very structured way in which things are worded to keep you out of legal trouble. And lawyers have a very crafty and structured way of asking questions so that they force you to give them the answer that they want to give. And I think it was lawyers who invented the language that goes into the description of hypothesis testing, because it's kind of written in such a way that you won't get in trouble for having said the wrong thing. So here we go. The null hypothesis, or what they call HO or H naught, it says that no difference exists between data sets, or there's no relationship exists between the data. So the null hypothesis says that all things are equal. It says that the waste in June, July, and August is not dependent on temperature and humidity. So right away, you know, our mind was telling us by looking at the graph that higher temperature and higher humidity means more waste. But our initial hypothesis is going to be that there is no relationship. The alternate hypothesis is, of course, that there is a difference between data sets, or that there is a relationship between temperature and waste. The p-value, and this is the big term. This is the final score. This is the rubber meets the road term. It's called, p-value stands for probability value. And it is the number, the score, that tells you whether or not the differences or relationships are not due to chance. In other words, the reason that you're seeing a relationship between high waste in the month of June, it's not due to just randomness. It's due to there is actually a cause. So it's defined as the probability of being wrong if we accept the alternate hypothesis, which is a roundabout way of saying that the p-value is the probability of being wrong if we accept, or if we reject the null hypothesis. And remember, the null hypothesis is what? It means that all things are equal, there's no relationship. So the p-value is the probability of being wrong if we reject the fact that temperature doesn't have an effect on waste. So, you know, a lot of people, you know, their brains start to, like, you know, swirl around and start to explode, and as they're trying to process this, and some people need to get a pen and paper and keep track of this, because what they're avoiding saying here is they're not saying that the p-value tells you that there is a relationship. It's telling you that I can't reject the, you know, I can't reject the fact that there is no relationship. So I'll kind of illustrate this a little bit further. So the basic logic is presume there is no difference and check to see if the data provides evidence that there is a difference. And if the evidence is that there is a difference, then you reject the hypothesis that there is no difference. In other words, you can't tell me that there's not a difference because the evidence, the data tells me otherwise. So the way hypothesis testing goes, we collect data and then we calculate the p-value. And this is all done in the statistical, you know, software package. The p-value is based on a probability distribution. And there's some terms here that you don't need to, you will learn if you continue on and learn more about statistics and Six Sigma. But what the takeaway from this, and this is the fundamental learning, and I tell all of my Greenbelt students, if you go out to if you want to get a Six Sigma tattoo on your body, then this is the thing you need to have tattooed, so you always remember it. Small p-value, H naught is rejected. Large p-value, H naught is not rejected. In other words, if the p is low, the null must go. And what we mean by a low p-value, if the p-value is less than 0.05, the null must go. If the p-value is high, the null gets by. So in other words, if you do the calculation and the final score comes out to be less than 0.05, say for instance it's 0.02, then the null must go, which means you reject the null hypothesis, which means you reject the notion that all things are equal, which suggests that things are not equal. One is different than the other. So if you did the analysis on waste levels in the month of June, July, and August, and your hypothesis was that temperature and humidity don't make a difference, and you ran the statistics and it came back with a p-value of 0, then you reject the notion that temperature and humidity don't make a difference, and you would draw the conclusion that temperature and humidity are making a difference. If the p-value in that analysis comes back greater than 0.05, say for instance it comes back as 0.42, that does not mean that temperature and humidity don't make a difference. What it means is you don't have enough evidence and data to prove that temperature and humidity make a difference. It's possible that if you had more data, you would be able to draw that conclusion. But what it's saying is you don't have enough data to prove, or you were unable to prove that temperature makes a difference with the data that you have. So it doesn't mean that temperature doesn't make a difference. It just means that you weren't able to prove it. And once again, if you think about a court of law, you are innocent until proven guilty. So being innocent is the null hypothesis. And until somebody proves that you're guilty, you're innocent, no matter how guilty you might be. The data's got to prove it. And that's kind of the concept between hypothesis testing. And when the p-value is less than 0.05, it means there is sufficient data to suggest that you are not innocent. If the p-value is greater than 0.05, it means that they didn't prove that you're guilty. You might still be guilty, but they couldn't prove it, not with the data that they had. Questions so far? So we actually go through and we talk about this, as we kind of expand on the meaning of the p-value and hypothesis testing and which side to err on. So we actually go through like an example of if you need to make a mistake, what kind of a mistake would you be willing to make? So for instance, you ask the question, if a person is going through a metal detector at the airport, and if the person doesn't have a gun in their bag and the metal detector goes off, so they don't have a gun and the metal detector goes off, that's an error on the metal detector, and it's a certain type of risk associated with that error. Or you could have a situation where the person has a gun and the metal detector doesn't go off. And the question is, which risk is better for you to take? Is it better for you to say that the person doesn't have a gun when they actually do, which means you potentially let a gun onto the plane? Or is it better to say that the person has a gun when they really don't, and now you're holding up the person at security? And most people would argue that, well, you don't want the gun on the plane, so it's better to make the error in the case of saying that the person was guilty of having a gun when they really weren't. But that's not always the way in which that decision should go, because like if you're in a criminal case and you find a person guilty of murder when they're really innocent, and you put the penalty for that is the death penalty. Now you're putting somebody to death who actually was innocent, in contrast to somebody who actually committed murder, but you found them innocent. And now you're setting free somebody who was guilty of murder. Neither of these scenarios is desirable. But if you had to make one mistake versus the other, which way would you go? And so the way you assess the risk is, do you put the risk on shipping out a product that's defective and putting the risk on the hands of your customer? Or do you risk throwing away good parts in your factory and losing money. So that's kind of the practical implication. And it's all driven by how you set up your hypothesis tests and the resulting scores. I'll say one more thing about the p-value, and I'll go back to when we talked about graphs. So the key to data analysis is understanding how your data is distributed. We talked about the histogram, and everything comes down to whether or not your process is on aim, which means are you meeting your target, and how much is the spread of your data? What's the standard deviation? And the histogram shows us that. And we use data to calculate process capability. Well, one of the things I didn't mention when we talked about PPKs and CPKs, the only time that those analyses are valid for your data is if your data follows a normal distribution. Now, I won't go into a lot of detail about normal distributions. You get more into that when you actually work, go into Greenbelt training or continue on your work with statistics. But normal distribution just means that you have an equal number of, it kind of basically means you have like an equal distribution of numbers that are higher than your average versus numbers that are lower than your average. It is truly like a bell-shaped distribution. If you don't have a bell-shaped distribution, if you don't have a normal data set, then the PPK and CPK calculations are erroneously or disproportionately influenced by the outlying data results. So that's why it's one of the most important things that you do in your data analysis after doing a histogram is you do a box plot so that you can identify and eliminate outliers. But you need to have a normal data set, and one way to calculate whether or not your data set is normal without just looking at it and trying to draw a conclusion based on your visual appearance is you run a probability plot. So after you use a histogram to look at your data, you do a probability plot, and the probability plot actually has as a part of the graph, and I'll show it at the end of the class just to kind of show you what this looks like. It actually has a p-value associated with it. And if that p-value is less than 0.05, it means your data is non-normal, which means you need to fix it before you go on to use it for like a PPK probability analysis, whatever. If your p-value is above 0.05, it means your data is considered to be normal. So the null hypothesis is that your data is normal. The p-value low means your data is non-normal, and now you probably need to call for help to get somebody to help you figure out how do I clean up my data so that it's usable for other analyses. So I'll go back at the end of the class just to kind of show you that probability plot, just to show you where the p-value is, just so that you get a visual picture of how the program gives you this score. But like I said, this slide here is the main summary that you need to be able to remember, because this is the ultimate kind of judge of results in statistics. If the p-value is low, less than 0.05, then you reject the notion that there is no difference, that everything is equal, that something is going on that you need to be aware of, or that this is a factor that's important. If the p-value is high, then you don't have enough data to show you that there is a difference. And I'll give you one more example to illustrate this. So if you flip a coin, and you flip a coin 10 times, and you count the number of heads and tails. So if you flip a coin and you flip a coin 10 times, and you get 6 heads and 4 tails, would you say that there is something odd about the coin? I mean, what are you expecting when you flip a coin 10 times? What result would you expect to get?
I would expect it to be halfway heads and tails, like 5 times heads, 5 times tails.
If you flip a coin 10 times, you expect to get 5 heads and 5 tails. But if you get if you flip it 10 times and you get 6 heads and 4 tails, you're now getting 60% heads. So the question is there something wrong with the coin? And people would say no. Okay, so if I flip the coin 100 times and I get 60 heads and 40 tails, is there something wrong with the coin?
Not
So now
necessarily.
So some people say not necessarily. Some people are starting to question it. If I flip the coin 1,000 times and I get 600 heads and 400 tails, is there something wrong with the coin? And the answer is yes, there is. And the interesting thing is, in each case, the ratio of heads to tails is 6-4, right? So why is, in one case, you say there's really no difference, but in another case, you say there's absolutely something going on here. And it totally comes down to sample size. And what'll happen is if you run a 2-sample t-test, or on that data, and you put in a 6 and a 4, it'll give and say, is there a difference in the coins? It'll give you a p-value of, say, 0.62, and I'm just making up that number, okay? Which says that the null gets by. You can't conclude that there's a problem with the coins. If you put in 60 and 40 and run the same calculation, interestingly enough, you get 0.059, which is just above 0.05. So you're starting to kind of like squint your eyes a little bit and scrunch your face up. You're not quite over that or below that 0.05 threshold, but you're getting awfully close. If you put in 600 and 400 and run the p-value comes back as 0.01, which that tells you that these coins ain't equal. Something's fishy going on here. All right. But the reason that it didn't show that for the first time the ratio was 60-40, because it was just 6-4, it basically says you didn't have enough data to show you or to prove that the coins weren't fair, or that the coin wasn't fair. But if you had more data, you might be able to prove that it might show that the coin is actually unfair. Make sense? Questions? Comments? So the key here is that.
Well, quick question. Oh, I'm sorry.
Go ahead.
So I know just in terms of a numbers case, you can say that there might be something wrong with the coin. If you do it 1,000 times, you get 60% heads versus 40% tails. But is there like any room to consider that maybe it's the way you're flicking the coin?
Right. I'm not saying that the coin is bad. It could be the way that the person is flipping it. It could be, but the point is that there's something non-random going on here. There could be a magician who's got a special way of flipping the coin to get a certain result. But the point is that something's going on. Something is causing that coin to have a higher probability of coming up heads than tails. It's not a random occurrence.
Oh, gotcha. Thank you.
Other questions or comments? All right, so let's so now we can use the hypothesis testing to confirm whether or not the stuff that we're seeing in graphs is actually true, and it's factually saying that these are factors that are critical. We can use it to prove a number of different things, but hopefully, between the cause and effect matrix, hypothesis testing, and other things, we're able to now take this extensive list of X's and narrow it down to a few X's that will be taken on into the improve phase. So I want to here just give a brief introduction of a very key topic that's a way to that's used in the improve phase, and that is called design of experiments. Now, there's a variety of ways that people approach experimentation. And the most classic approaches to experiments is you test out one factor at a time, or you change many things at once. The problem with testing things one factor at a time is, one, there's no guarantee of finding the optimum settings. There can be interaction of variables that can produce incorrect conclusions, and it's very time consuming and inefficient. A planned design of experiment is optimum because it looks for the optimum methodology, and it's statistically verified and documented. And it takes into account interactions of variables that are incorporated into the design, and it makes it more efficient and effective. And DOE is a preferred methodology to develop a mathematical model, y equals f of x, 1, x2, f, whatever, which is a thing that we're trying to do with Six Sigma, is we're trying to establish a relationship between x's and y's, and to determine the best configuration of a combination of x's that gives you the desired y. And I'll just say this, when we get to this part of the training in the Greenbelt class, and we go through an exercise in training where one of the good or fun hands-on exercises we go through is a Statapult. And it's an exercise to help you understand the concepts that we're talking about here in Six Sigma. So the objective is you have this catapult, this like wooden catapult that launches a rubber ball and shoots it across a room. And the objective is for you to be able to take this device and to pull the catapult back, and it's, has a rubber band that you stretch out, and you let go, and the ball flies across the room, and you're trying to hit a target like 2 or 3 yards away. Okay, you're trying to hit a very specific target. So initially, you try to launch this ball and to make it go a very specific distance, and balls are of course flying all over the place. Now, during the course of Six Sigma training, as you're learning about measuring and data and process capability and understanding X's and Y's, you finally realize that there are some things some factors that are important to dictate how far this ball is going to travel, and also how you measure how far the ball travels and that kind of a thing. So the final exercise is you then identify these 3 or 4 key factors, and you run a design experiment that essentially helps you calculate this function, saying that the distance that the ball is going to travel is this equation, which is you stretch the rubber band out this far, you do this, you have this setting, you have that setting, and then you test it out. And literally at the end of the class, you're able to take this device and shoot a ball across a room into a coffee cup 3 yards away. And people it just kind of like blows their minds to be able to see that how precisely they are now able to control, launching this ball across the room as a result of having to develop this mathematical model through running design experiments. So this is where people get all super excited and all geeked out about Six Sigma and want to do it for the rest of their lives, because this is just like absolutely amazing how this works out. So I'm just going to introduce DOEs and kind of talk about the concept, and hopefully, as you evolve your skills in this area, you will take the opportunity to learn more about it, and especially if you're doing research, actually use a design experiment. So here's a classic approach to an experiment where you're looking at one factor at a time. So you want to improve gas mileage, and you want to evaluate gas type and timing settings. So you have, say, 2 types of gas 1 and gas 2, and you have 2 settings for your timing, T1 and T2. So initially you run a test with gas type 1 and timing setting 1, and you get 30 miles per gallon. Then you rerun the experiment and use gas type 2 and timing setting 1, and you get 20 miles per gallon. So what conclusion do you draw from that? Well, you say, well, gas type 1 is the best. So you're now going to use gas type 1 for further experimentation. So now you want to confirm which timing setting is best. So you use gas type 1, timing setting 1. You get, of course, you got 30 miles per gallon the first time you ran that. So now you run gas type 1 and timing setting 2, and you get 25 miles per gallon. So what's your conclusion? What's the best combination of settings? And in this case, you say we use gas type 1 and timing setting 1, and you're going to get 30 miles per gallon. So that's the conclusion that you draw, that this is your best setting for getting the most gas mileage. And it kind of makes sense, except for you're missing something. Had you run a full factorial design experiment and tested each of the 4 combinations, you just basically tested 2 combinations and then added a third combinations, what you would have found is with G1, T1, you got 30 miles per gallon. You ran G1 and T2, you got 25 miles per gallon, and you ran G2 and T1, you got 20 miles per gallon. But the thing that you didn't test was gas type 2 and timing setting 2, which would have gotten you 45 miles per gallon. So he said, well, what went wrong here? What you missed in running this one factor at a time experiment was the interactive effect of gas type and timing. These 2 things interact, and the effect of one factor depends on the level of the other factor. And therefore, you missed this optimal data point using your one factor at a time approach. If you think about baking a cake, and the 2 key factors are oven temperature and the amount of time you spend in the oven. There is an interactive effect between oven temperature and time, where the time that the cake needs to stay in the oven is dependent on the oven temperature. They're not independent variables. They interact with each other in such a way that if you're measuring the cake by, say, use your criteria, moisture level in the cake. So I want a nice moist cake. So which combination of temperature and time is going to give me a cake that's very moist without being soggy? Well, if you don't run a designed experiment, if you just do a one factor at a time experiment, you won't find that optimal temperature time ratio. So this is why running DOEs are important. The other approach that people have to experimentation is they change many things at once. And this is what happens when teams when their teams get together to solve a problem. They brainstorm a bunch of possible ways to improve the process. They prioritize the ideas, and then they implement as many high priority ideas as they can all at once. The problems with this approach is you won't know which changes are responsible for the changes in the result, or you may keep doing something that is actually harmful to the results. And it's impossible to understand the cost-benefit considerations for each individual change. Here's an example. A team needed to increase sales and profits of an existing product. So you get everybody in the room together and they brainstorm, how can we increase sales? So they doubled the advertising budget, because that was a good idea. They started doing telemarketing to both old and potential new customers. Seemed like a good idea. They lowered the price by 3%. They figured by lower price we'll get higher volume in sales. They added 3 new package sizes, saying customers want variety. If we offer them more different sizes, we'll get more sales. They sent technical reps to large accounts to discuss new uses. They took very large accounts on entertainment trips, so that we, wine and dine the big customers. They'll buy more. And the engineers found a way to lower the level of impurities on 3 of the products to improve the quality. So sales went up 10%. But all of these factors cost money. So the question is, of these 7 things that they did, which ones had a good effect? Did some of these actually hurt sales? Did some of these factors have no effect? Or was the increase in sales totally due to something else? The thing is, they'll never know because of the way that they went about implementing the changes. So there's a risk in changing multiple things at once. Now, you could have designed an experiment where you took into account 7 different factors and statistically set up the combinations of changes in such a way that you could then determine which of these factors, or more importantly, which combinations of factors impact sales, such that you could have determined that, hey, actually, if we increase the advertising budget by 22%, if we lower the price by 2%, and if we actually increase the quality by lowering the level of impurities by 5%, then sales would be predicted to go up by 37%. So you could have actually run you could have designed an experiment and then run a number of these conditions and measured sales and determined which of these factors or which combination of factors actually make a difference. But by doing all of these things at once and then not differentiating between them, you don't know which of the changes actually made a difference and which may have even, like I said, some of these could have actually even hurt sales. So it's important to have proper experimentation. And I'll give you just another kind of funny story to kind of leave us with about how somebody might approach experimentation. So let's consider the case of a certain person who decided he wanted to investigate the causes of intoxication. Well, he drank copious amounts of whiskey and water using a 3-to-1 mixture, and of course became highly inebriated. The next day, he repeated the experiment, holding all variables constant except one. He decided to replace whiskey with vodka. Again, he became highly inebriated. On the third day, he repeated the experiment for the last time. On his third trial, he used bourbon in lieu of the whiskey and the vodka, and the result was the same. He became highly inebriated. So what was the conclusion that the person drew from this? After recovering, he concluded that the water causes intoxication because it was the common variable. Basically, that's just a little parable to highlight the importance of using proper experimentation. And as you go down the road, design experiments is the way to go in terms of testing for possible, how various factors can be modified and adjusted to give you optimal process improvements. Quick questions on what I covered. And just like I said, it's just a high-level overview. We're not actually, running an exercise here, but just kind of putting the concept out there. Any quick questions? I'll quickly run through this topic in the improve phase. Besides using proper experimentation to draw the right conclusion and figure out how to actually adjust your X's to give you better performance. I'll talk about mistake proving, because this gets us back to the thing we talked about on day one about applying lean techniques to reduce the likelihood that you have errors and things like that. Mistake proofing is basically preventing errors before they occur. It's like taking out in some cases, taking out the human element to prevent mistakes. In Japan, it's called poka-yoke, which is a Japanese term for mistake proofing. First thing to understand, what's the difference between an error and a defect? An error is a deviation from the intended process. All defects are caused by errors, but not all errors result in defects. So errors is you make a mistake. Defects is you end up with a bad result. Defect is a deviation from specifications. Therefore, parts with defect do not meet customer expectations. Why do mistake proofing? Is to eliminate defects which add cost to the product, increase product process and product robustness, eliminate opportunities for human error. You use it to address risks identified in a process in which the consequences of an error are expensive or dangerous. A process step has been identified where human error can cause mistakes or defects to occur. Some mistake proofing techniques. Implement simple, using like fixtures, jigs, gadgets, or warning devices to prevent human error. Fixtures is like you can only fit it into this thing. It won't fit into the wrong type of space. Standardize the process and thoroughly document the procedures. You may have heard of standard operating procedures. Part of that is so you have a specific set of instructions that as long as you follow those specific instructions, the process will turn out right. You optimize the environmental conditions, the lighting, the ventilation, the temperature to increase the comfort level of the people to make them less prone to making mistakes. Detection-oriented mistake proofing to ensure 100% error detection. Use automatic inspection where 100% of the errors will be detected. Use electronic sensors to activate warning lights, buzzers, color-coded parts and graphics, and things like that. Some mistake-proofing techniques. Since we just finished Thanksgiving, that little pop-up thing on the turkey is designed to help you know when the turkey is finished cooking. So when that little thing pops up, the turkey is done. We won't use the iPod Shuffle anymore because you guys probably don't even know what that is. But there's warning lights in the dashboard of your car, numbers of warning lights to let you know that something is wrong with the car. Here's an interesting one. I didn't realize this until I started studying Six Sigma many years ago. The car manufacturers, there's dipsticks in your engine. There's a dipstick for your oil and there's a dipstick for the transmission fluid. The dipstick for your oil, the handle on it is round, so you stick your finger in and pull it up. The dipstick for your transmission fluid is shaped like a T. I knew that I always knew where the oil was and I knew what the transmission fluid was. It didn't dawn on me that, the reason that you have this loop in the oil dipstick is because it's made to look like an O for oil. And the transmission dipstick has a T-shaped handle because it's for transmission fluid. But these are just some things to keep you from making the mistake of, putting oil in your transmission fluid or vice versa. Let me just quickly go to just another quick summary. There are various mistake-proofing techniques. There are things to shut down a process before things go wrong. Like for instance, some cameras won't function if there's not enough light to take a picture, or like my dryer has a device that shuts down when it detects overheating. Like if you put tennis shoes in there, then it may detect that the shoes are overheating, and shut down. There's control techniques. Like for instance, the unleaded pump hole for the gas tank is smaller than the ones for diesel gasoline. So that way, if you go to a gas station, you can't put the nozzle for the diesel gas into your car because it's made bigger, because you never want to put diesel fuel accidentally into your regular car engine. Or apples are passed through a sizer, and those that don't make it the size requirement, they get sent to the discount outlet. Or there are warning techniques, like systems that alert the driver that not all the seat belts have been fastened, or smoke detectors that provide a warning that smoke has been detected and there's a possible fire. So a variety of mistake-proofing techniques to either shut down the process, control the process, or warn you to prevent people from introducing errors and variants into your processes. So this is another part of the improve phase. So once you figure out what factors can cause your process to go wrong, implementing methods to prevent those errors from occurring. Questions or comments? Okay, we'll quickly go through our one final topic, and that's the control phase. Give me just 5 seconds here. Okay, so we've done all this work. We've gone through, we identified what our customer needs. We turned that into defining the output of our process that controls the customer, what the customer needs. We measured to see how we're performing today versus the customer specifications. We calculated our process capability. We then go into the analyze phase where we've identified this exhaustive list of inputs that potentially impact our project Y. We've run through some techniques and some things to help us prioritize that list of inputs and come up with the vital few inputs. We ended up with a list of like 5 or 6 variables that are critical to controlling our final product output. We ran some design experiments to come up with the optimal set of settings for those variables or controls for those variables, so that now we know how we need to run the process to consistently get the right result. And we're going to implement some other controls to make sure that people don't mess up the process by changing the knobs that they're not supposed to. So now we want to control our gains. We've demonstrated that we can improve the process. How do we then control to make sure that everything is sustained? And we'll talk about control charts. So control charts is part of a science of what we call statistical process control, or some people call it SPC. So we know what statistics are. It's a science about gathering facts based on numbers and frequency, drawing general conclusions. We've talked about what a process is, a series of successive activities with a cause and effect relationship, and the combination of variables needed to manufacture a product. And now control is keeping something within the limits. Definition of a control chart. It's a real-time method that aims to control a process to minimize variations and prevent defects, where the actions of operators are based on statistical evidence related to the stability of the process. So in other words, these are essentially graphs that are established to prevent people from making adjustments to a process that are either unnecessary or unwarranted, or that are not based on statistical evidence. So it uses an ongoing sampling of your process to establish whether or not your process is stable. Now, there are causes of variation. I mentioned this earlier when we talked about the run chart, and we saw that in the time series graphs, there were some spikes in the data, and these spikes were what we call special variation. Well, there are 2 types of variation: common cause variation and special cause variation. And common cause variation represents basically like 85% of all problems. They are not solvable right at the point of the process. These are the things that this is what you're actually trying to do with a Six Sigma project. You're trying to understand the sources of common cause variation to see what are the things that happen on a day in and day out basis that cause you to have variability in your process. And if you can understand those common causes, then you can control them better and make your processes more consistent. Special causes are stuff that are specific to a machine, operator, raw material, or method of measurement. The operator can find these things and detect and correct them, and they account for about 15% of the problems. They need local actions. These are like special events that happen. A high-level example is, so if you're running a process and you produce 10% defects on an annual basis, and on a week-to-week basis, your waste you may have a great week where you only make 4% waste, and you may have a bad week where you have 15% waste, and it kind of fluctuates back and forth between those 2 levels. Well, there were a couple of times in the summer where you had a week where there was like 40% waste. Okay. Well, so what happened? Well, it could have been that a storm came through in the middle of the summer, and a hurricane came through the area, and there was a complete plant power outage, and all the equipment went down, and all the product that was made that day went to waste. And the next day you had to do a lot of work to restart the factory, and you made more waste. So what happens is, when you look at your weekly waste numbers for that particular week, waste numbers were abnormally high. And it wasn't because of anything normal in your process. It was because a hurricane came through and shut down the plant. So you deal with that as a special cause. and the way you fix that is, maybe you put in a backup power system so your power won't go out or something like that. But that's not going to get fixed by doing a historical analysis of your process and seeing what little things cause variation from day to day. So special causes is that catastrophic thing that happens, or a machine just all of a sudden fails, or it starts to deteriorate. And you may realize that, oh, this machine needs to be replaced because it's old. So the fact that you're making an elevated waste level is not because your process in general is bad, it's because you got a bad machine. So to further illustrate the concept of special versus common causes, just kind of go through a brief exercise. So if you guys happen to have paper and pencil handy, or pen and pencil, or something to write with and something to write on. And these days I know it's kind of tough because everybody writes in their phone. But if you happen to have something to write with and something to write on, then try this exercise. Okay, so what I want you to do is take the pen and paper and sign your name 5 times. So sign your name, 5 times on a piece of paper. And when you do that, look at the signatures and tell me whether or not the signatures are the same. Are all 5 signatures the same? So everyone's saying that they look at their 5 signatures and the signatures are not the same. Okay. So was the variability between the signatures caused by common cause or special causes? So let's try this. Put the pen in the other hand and sign your name 5 times with the other hand. Now, once again, are the 5 signatures the same? Most people can't even recognize them as signatures. So here the question is, again, is the difference between the 5 signatures that you wrote the second time, is that common cause or special cause variation? Actually, the answer is it's common cause variation. So the difference between the 5 times that you sign your name with your right hand is common cause variation. The difference in the 5 times that you wrote your signatures with your left hand is common cause variation. The difference in signatures between your right hand and your left hand is special cause variation. Think about that a minute. So writing signing your name with the same hand time and time again, you're going to have variation because you're not, and if you really tried hard, and if it's important for your signature to look the same each time, you could put some effort into it, and you could probably control your handwriting so that it was more consistent and reduce the variability. That's all common cause variation. You could do the same thing if you broke your right hand and you had to all of a sudden start writing left-handed. You would eventually get to a point where you could write your name pretty consistently so that each time you wrote your name with your left hand, it would look kind of the same. That's once again common cause variation. But if today you write your name once with your right hand and write your name once with your left hand, they're going to look vastly different. And that's because you have special cause variation. That kind of illustrates that concept. So the question is a special cause variation when the control variables are changed. It can be. It just means that some things, no. the special cause variation is when something has fundamentally changed in the process. Something has disrupted the process. You can fix special cause variation by altering or readjusting the control variables. But the reason for the special cause variation is because something has happened in your control. And it can be because somebody changed the setting. Let's look at a quick thing about, so this is kind of the conclusion of the signature exercise, okay? Let's just quickly talk about control charts. So here is, we'll show you a control chart, and this is where we react to common cause as if it were a special cause. So this is our process. This orange line here is the data from our process on a day-to-day if we just let it run. If we just let it run its course, all right? So we're measuring hose external diameter. The control limits are the red lines. The specification limits are the blue line. So we have to always stay within specs. And what we're seeing right now is the process is between the red lines. So we're in control. So what we see here is follow the blue line now. After here, somebody makes a process adjustment. Why? Because they saw 3 data points trending upward. So they made a process adjustment to bring the process back down, which results in this. So now they see, oh no, the process is trending downward. I need to make an adjustment. So they make a process adjustment, and now the process goes back up. So they say, oh no, the process is trending upward. I need to make a process adjustment. So they make another process adjustment, and it comes back down. Then they make another process adjustment, and it goes back up. So notice, by responding to the short-term trends and making adjustments to the process, they actually introduced variability which normally would not have been there. So this is the kind of the point in the science behind control charts. So for a control chart, you have an average chart, and this gets back to, in Six Sigma, we're dealing with averages and standard deviation. An average chart measures the level of accuracy. An amplitude chart measures the degree of precision or the degree of variation. So in a control chart, and when you generate control charts in a statistical software package, you essentially get 2 graphs. You get the chart on top, where it's looking, where if you look at the range of values, the diameter is supposed to be between 14.1 and 14.2, and you can see the level of control. The bottom chart shows you the level of variability of your process. So what you're seeing there is over time, your variability increases. Now, what control charts do is they actually perform a series of statistical tests, and they give you a signal that tells you that something is wrong, so that you need to make an adjustment. And there's like over a dozen different tests that you can have in your control charts. Here are some of the basic ones that are very common. The first test is if you have a point outside of your control limits, which means you have a value that's 2 or 3 standard deviations away from your mean. It says that something special has happened to cause your process to behave abnormally, and you need to do something to fix it, because something has happened to cause your process to go out of control. Test number 2 is kind of interesting. It says 7 points in a row on one side of the mean. Now, to some people, they may look at this and you look at the blue dots and say, this process looks very stable. The problem with this is that you would expect a process to be, if this green line represents your mean, you would expect a process to have values above and below average. What's happened here is you now have a process that consistently runs below average, which is not normal. And it's the result of somebody made a process adjustment back here that caused the process to be stable, but you're now running below average. The next test is 6 points in a row trending up or down. And notice it says 6 points in a row because some people may be tempted after just 3 points in a row to make an adjustment. And that's where you cause variability, you add variability which shouldn't be there. But if you get 6 points in a row, either going up or down, then you have a need to adjust your process because something has shifted in your process that's causing you to now be on an upward or downward trend. Another classic example is if you have alternating points, one above average, one below average, the next one above average, the next one below average, the next one above average, the next one below average. If you have that kind of cyclical behavior, that's not random, that's not normal. And it may suggest that you have like a 2-shift operation. Your day shift is giving you one result, your night shift is giving you another result. You know, one person's signing with their left hand, one person's signing with their right hand. So bottom line is these control charts have built-in tests to let you know when there are special causes that are disrupting your process that need to be adjusted for. So these processes are both stable and in control. I'll make one final comment on this to kind of wrap this up, because there's two concepts that we've been talking about here. With control charts, we were talking about process stability. Earlier, we talked about process capability. They are two independent properties. Process capability is the ability of your process to make product that is within that meets your customer specifications. Process stability is your ability of the ability of your machines and your equipment to make a product consistently. For instance, these are limits of the control of the process, these red lines here. So you're looking at examples of a stable process here. And the red lines are calculated based on the history of your process. Here at the bottom, you have processes which are not stable. Okay, so on the top, your processes are stable. At the bottom, you have processes that are not stable. However, if we now add the customer specifications, so on the top, we have processes that are under control and stable. The bottom, we have processes that are out of control and unstable. If we now add in customer specifications, those are the green bars, okay? So what we're seeing on the top, in the upper left-hand corner, we have a process that is both stable and within specification. On the right-hand side, the process is stable, but it's not meeting the customer specs. This is like having a truck that is too big and you're trying to fix it and fit it into a tight parking space. So no matter how good your parking skills are, if the parking lines are narrower than your truck, you're not going to be able to fit it in. Below in the lower left-hand corner, the process is unstable, but because the customer specs are really wide, the customer will take anything, you can get away with it. At the bottom, the process is neither stable nor in spec, and you just got a hot mess. So this is just quickly to help us to understand and put in context that at the end of the day, we need to deliver product that meets specifications. It needs to be within the green lines. And process capability is the calculation that tells you whether or not your process is able to meet specification. Stability tells you whether or not you have special cause variation that is impacting your process. So control charts are there to essentially evaluate whether or not you have special cause variation that's impacting your process. All right, primary purpose of control charts is to distinguish between common cause and special cause variation. The variation of the process that is in statistical control is associated with common cause. It can only be reduced by improvement projects to the process. Special cause variation, you have to do an investigation as to what is the source of the signal, what caused the special cause. So, quick summary. What is lean? So quickly, what's the definition of lean?
Reduction or elimination of waste.
Reduction or
Oh.
elimination of waste. What is Six Sigma?
Reduction of the variation.
Reduction of variation. What does DMAIC stand for? What's the D stand for?
Define.
What's the M stand for?
Define, measure,
What's the A stand for?
analyze,
What's
Analyze.
the I stand for?
improve, and
What's the
control.
C stand for?
Control.
What does CTQ stand for?
Critical to quality.
Critical to quality. That's what the customer wants. What's the important document that's needed to define a project?
Charter,
Project charter. How do you define what's your primary metric? Yeah, primary metric, consequential metric, secondary metric. What's your primary metric?
Primary is your why?
That's your project Y. That's the defect you're trying to fix. What's the secondary metric?
the small wise,
Nope.
It's the X's.
It's an additional. It's not your X's. It's also an output. Secondary metric is an added benefit. You're looking to reduce variability in the length of the hose that you're making, and as an added benefit, you are reducing your waste disposal cost because you're making less waste. What's a consequential metric?
Consequential is the result.
other things that might impact that process.
Other negative things. It's unintended consequences of trying to do the right thing. What do the letters in SIPOC stand for? What's the S stand for?
Supplier,
What's the I stand for?
Input.
What does the P
Input.
stand for?
Process,
What's the O stand for?
outputs,
What's the C stand for?
customer.
Customers.
All right. Which two statistical calculations can be used to describe any distribution?
The mean and standard deviation.
The mean and the standard deviation. Very good. So what's the letter for your project defect, your primary metric?
why,
Okay, what are the two types of data?
Continuous and I forget the other one. Good. Yeah, and district.
Continuous and discrete. Okay. What index is used to quantify process capability? What is that called? Somebody asked about it at the beginning of the class.
The CPK.
CPK.
CPK and PPK. All right. What is the p-value criteria for which you reject the null hypothesis?
Probable value. Who knows?
What's the value?
0.05.
Okay, so the P is low, the null must go. So if the P is less than 0.05, you reject the null hypothesis. What does DOE stand for?
Design of experiments.
Very good. Are control charts primarily used to track common cause or special cause variation?
Common cause.
You got a 50-50 chance of getting it right. Control charts track special cause variation.
And go ahead and come off of mute if you are answering, just to make it a little easier and speak.
So keep that in mind. Control charts tell you when you need to make an adjustment to your process, and you only need to make an adjustment to your process if something weird is happening, some special cause. You don't want to adjust your process due to common causes. You want to make that's why you do the Six Sigma projects. You figure out what are the common causes, the long-term fixes that you need to put in place to reduce your variation. Special cause variation are like alarms that go off because something's going wrong right now. And that's what control charts help you pick up. All right. These are the types of questions that you may see on the exam. Tony will send this out to you after today. It'll be like a 30-question exam. You'll have, we'll get you to send them back to me by the end of next week. And along with that, you'll also get a survey that you will need to fill out about your assessment of this course. And like I said, Tony will send out both of those to all of the people who are on the mailing list after. This pretty much wraps up the class. I'll pause for any additional questions or comments. I know some of you guys have to leave. I'll stick around for a little while longer. So if you have questions or comments, either I've got answers or I'll make up some.
Are we receiving the exam right after this?
Yes, I've got to send out the latest version to Tony and she'll forward it to him.
Right. So let me just clarify. If you have made both classes, at least one of the prior two classes, or made another arrangement where you will receive the exam, just because you logged in doesn't mean you're going to get the exam, because you do have to have a certain number of hours involved and completion of it. So we have things we have to verify because this is being offered by a grant. So that's why I was asking you to register and show evidence of participation, because we may have to show that as well.
I see in the chat that Brian has just put in the initial release of the survey. That's good.
Right. The survey link is in the chat. This is a class survey. Brian Jackson has posted that in there, so you can go ahead and take that. And like I said, there were a couple of people who joined today for the first time. I don't have any record of you attending any of the other classes and don't have any information on how to contact you. So Brian's going to try to reach out to you. I want to say Kayla was one of them, Weber, and the other one was, I think her name was Sandra. But yeah, if I don't have any record of you attending, then you're not going to be able to take the exam. Any prior record?
Also, a quick question. My chat for some reason is not working. So the survey will also be emailed.
Yeah, I'll email
well,
it.
right?
Yes. Yes, I will
Okay,
email it.
thank
I know
you.
for some people, Teams platform is quirky, so you may not be seeing everything in the chat. And yeah, I will send that via email. We would like for you to we'll send it out today and would like to have that back by a week from today. So we'll put that in the email as well. And I will also, upon completion of the class today, upload the videos. It does take a little bit of time to do that. So you might not get them until tomorrow because I have to literally download it and it takes maybe an hour for each one of them. So it's a little bit of a workaround. So I will put those out there if you want to go back and use that for studying. And everyone should have the PDF. The Eventbrite page is the landing page. It has the links for the videos and the PDF, and I'll drop that in the chat just in case you don't have it, but that's also been sent out an email. Does anybody have any further questions? If not, we'll go ahead and end. We can stick on just for a few more minutes, but just want to make sure you have everything you need to be successful after today. I'll be hard to connect with next week, so please speak up if you have any questions.
Thank you guys so much for this wonderful opportunity.
Yeah, thank you, Keandre.
Pleasure.
Thank you all for coming. This came as out of a conversation with some of the A&T students at the Fall Comfort Zone in NC State. And as a result, we were able to pull this together with some funding that was provided by a grant. So thank you all for doing that. That was a quick question. I saw a hand up.
Hey, sorry, I did want to just ask a quick question on the exam. So is that just going to be, we're going to be emailed a link and then we just take, is that exam like an online exam? Is it like Proctored or anything like that? Or is it kind of just something you just take on your own and send back?
It's something you take on your own and send back.
Okay. Okay, thank you.
All right. I'll stop the recording here and we'll hang around for a few more minutes. If there are any other questions, we'll do that. And also, I'll be talking to the Process Improvement SIG. So just a little knowledge about NSBE. I don't know if everybody in here is a part of NSBE, but if you're not, locally, we have the Research Triangle Professionals chapter. If you are a professional working, you don't necessarily have to be an engineer to participate. And if you're not in the Raleigh-Durham area, there are other chapters that you can be a part of, as well as just a general member. There is a NSBE conference that will happen in March in Atlanta, the 20th to the 24th. That's already on the NSBE site, nsbe.org. So that is a way just to kind of learn more about the organization as well. And if you are in a college environment and you're not a part of the college chapter, most likely there's probably one at your school. If not, you can still be a general member. But it is a good way to stay connected to knowledge like this. Not only does the Process Improvement Special Interest Group offer Yellow Belt, but we also have offered Green Belt training. We've also have webinars and live streams because we're in different places. So it's a national group. So we have things come up. We have a LinkedIn link. We're on social media. So if you want to stay connected to the programs and things that are being offered, you can do that. And we also have in the past had talks on data analytics, PMP, some of those career enhancing certifications and skill sets that keep you relevant. So just a little background on the Process Improvement SIG. Brian, if you're on and you want to chime in and say